So, welcome everyone to the last session of talks of the Beyond IID. So I think we have a great session ahead of us. I apologize if there is some noise in my background because I had some problems this morning with the flight, so I'm at your airport right now. But anyways, it's a pleasure to have Zoltan Zimboras from the Wigner Institute to talk about super-exponential distinguishability of correlated quantum states. So Zoltan, please, the floor is yours.
Thanks a lot, Daniel, and thanks a lot, Masahito and the SUSTEC team for organizing this Beyond IID workshop. And indeed, I'm going to talk about this topic, the super-exponential distinguishability of correlated quantum states. And we have an archive paper for those with the same title for those who are interested in the details. And this work was done together with Milan Mosonyi, who is, I think, here, and two of his PhD students, Gergely Bunt and Gábor Maróti. And they are from the Budapest Technical University. And yeah, myself, I'm from Wigner. So let's start with the main topic. Oh, sorry, something happened with my, okay, I will not touch it. So basically, I'm going to talk about hypothesis testing more precisely binary state discrimination, although we will also talk about like state discrimination that goes beyond binary a little bit. And of course, this is like a very, very, very standard topic within quantum information theory. Like the most treated case is, of course, the IID, state discrimination, where we are presented like with identical prepared quantum systems, either identically prepared n times rho, so we have rho tensor rho n times, or sigma. We have this hypothesis, and one is the null hypothesis, the other is the alternative hypothesis. And then the task is to guess, given a state, which hypothesis is correct. And of course, we can choose a two-outcome measurement, and which will two-outcome POVM, basically, which will determine what we will choose. And for this, oh, sorry, do you hear me now? I had some net problem.
Yes.
Yes. I can hear you.
But
Sorry for this.
Please share your screen. Can you please share your screen again? I think the screen is gone.
Yes, of course. I'm sorry for this technical problem. My net is not the best. Okay, so so we have this, just to repeat a little bit, we are in this binary state discrimination scenario with the IID states, so rho tensor n and sigma tensor n. And then the task is to choose a POVM such that the outcomes will be like that we make errors when reading of the outcome is small. I mean, what are the error types? Like there are the type 1 error, which is like that we say that the the null hypothesis is we reject it. We say that it's not the raw tensor n, although in reality it was that. And of course, the probability of that is given by this simple equation shown here. And type 2 error, when we accept the null hypothesis, H0, although it's false, and then it's given by this, also this is sigma tensor n. So this picture shows this these two scenarios, okay? And this is, of course, very well known, and it has been in quantum information theory, like really well investigated, what are the asymptotics of these errors. And in general, except for a trivial case, which I will talk about, the best achievable asymptotics is an exponential decrease to 0 for both of these error probabilities. And of course, there are many theorems regarding it, in like how we want to treat it. If we want to have if we allow for a finite error for one of the exponent, and then the relative entropy gives you the exponent of the exponential decrease of the other error. And if you have a symmetric case, then you also have this type of exponential decrease. And I mean, this is a really long topic, and many things are very standard, and many things are known. And there is only this trivial case, which is not about the exponential decrease when rho and sigma are orthogonal. So, okay, so this is the IID scenario, but of course this workshop is called Beyond IID. So let's go do state discrimination beyond IID. Okay, so I mean, natural scenario would be to consider states which are not anymore of the form like rho tensor n or sigma tensor n, but are states that are, we take an infinite spin chain, rho 0 and rho 1, and we restrict those states to n spins and consecutive to an n part of the spin chain, and then make a POVM there. And actually, this has been also studied in the literature already, and the results that have been obtained here in this non-IID or correlated cases also usually showing an exponential decay of the error probabilities of both type 1 and type 2 errors. And for example, a nice theorem also due to Milan and his co-workers is that if you have a translation invariant local Hamiltonian and you consider thermal states for that one, then those actually this type 1 and type 2 error probability decrease also exponentially to 0. But there are also other families of state where this happens. So our question was, when we were looking at this topic, was that, I mean, the question was that, okay, so in such a correlated scenario in general, can a qualitatively different behavior occur for the type 1 and type error? Like how the asymptotics of those compared to the usual IID case. Okay, but moreover, of course, this is like maybe we can come up with some weird example which has qualitatively different. So maybe some example also motivated by physics. Of course, local Hamiltonians are always a good example which is motivated by physics. And we have seen, as I mentioned, that thermal states of local Hamiltonians, for that the error exponents are again decaying exponentially only. And actually, what else is left? Well, the ground state. So it would be nice to know that for ground states of local Hamiltonians, can a qualitatively different behavior occur for the asymptotics of the type 1 and type 2 errors than in the IID case. And actually, we answer both questions, and our answer is yes. Actually, there is a possibility we give a particular set of states where the type 1 and type 2 errors have a different behavior, and I'm going to show some theorems around that. And also, actually, those states can arise as ground state or of two distinct Hamiltonians. And then you can make a super exponential state discrimination. So I give away our results in a short term, but let's go a little bit deeper into this. So the particular setup that we are considering is actually a setup that originates from fermions, so from Car algebras, canonical anti-commutation relation algebras, and actually quasi-free states on these algebras, which are states that we have a very good handle on and that we can consider that we can work with well. And I mean, of course, it's very technical, the setup that we will consider. So I'm just gonna put up some part of a description of this, but I'm gonna, but that's technical. Like I'm just gonna explain a little bit about this. So basically, here is a piece of text which I will explain. So basically, what we are considering is a fermionic chain. So this is the Car algebra belonging to the line, so to the one particle Hilbert space L2Z. And actually, it's very interesting that translation invariant states, more precisely translation invariant even states, can be translated can be actually translated to the spin chain language. So we can move them and build up a translation invariant state on the spin chain. It's done actually, well, usually physicists talk about this Jordan-Wigner transformation, which makes this, but this only works for finite spin chains. But for an infinite spin chain, there is a little bit more complicated way of doing this. This translation, which is like a generalization of the Jordan-Wigner transformation due to Arak. And okay, so when we have such an infinite state on either the fermionic chain or the spin chain, usually these are defined by expectation values of the local and quasi-local algebras, okay, of this Car algebra or the spin chain algebra, and this is so also with the quasi-free states. So basically, if we have on the one particle space of the Car algebra a positive semi-definite operator Q, which we call usually symbol, then we can define a quasi-free state using this Q in the following way, that we have for each vector in the one particle Hilbert space, we can define in the Car algebra creation and annihilation operator, and actually monomials of this creation and annihilation algebra, creation and annihilation operators, they generate a dense subset in this algebra. And of course, this means that if I can now define a state, if I give expectation values to these operators that are consistent, and one way of doing it is actually to defining these expectation values as determinants corresponding to this Q operator in this form. Okay, and if Q transformation invariant both on the fermion chain and then when we translate it to the spin chain, and in that case, all these translation invariant Q symbols can simultaneously diagonalize by the Fourier transform, which we define first in the one particle Hilbert space of the L2Z, and then can also be transferred to the full Car algebra. And actually, then it turns out that every translation invariant symbol Q arises as an inverse Fourier transform of a multiplication operator, multiplication by some function on this L2 0 to 2 pi subspace. Of course, where the function should be on 0 2 pi, and it should be almost everywhere between 0 and 1, such that the it will satisfy that Q is between actually the zero operator and the identity operator. And in the case when we are talking about pure states, for example, ground state of certain operators, then Q will be almost everywhere, like this MQ function or the small q function. Its multiplication will be multiplying with a function that is almost everywhere 0 or 1. Okay, so basically it means that it's a characteristic function, and pure translation invariant quasi-free states that are also number conserving, they are in one-to-one relationship with functions on 0 to pi that are characteristic functions. Okay, and this is this complicated setup, but just be with me, like I'm gonna give you the result and then interpret it in a physical term later. So basically, our main result is, and this we stated in a big generality, namely not in a binary, but actually in a multi, in a composite hypothesis testing way, is that suppose that we would have a set of quasi-free states, and these functions would be such that these qi functions belonging to one of the set of quasi-free functions states, and ri to the other set of translation invariant quasi-free functions would be such that there would be an interval mu such that qi would be 0 on this interval and rj's would be identities. Then actually yes, so then what we would have is actually something we would have it would turn out that we could do super exponential distinguishability between those two set of states. Okay, I mean, of course, if it's easier to think about just two states, one belonging to an interval, let's say 0a, the other belonging to b 2 pi, and a is smaller than b, then of course there is this then of course we can find that mu is for example 0 or a or 1 or b 2 pi would play this role of the mu interval. And moreover we also show that actually this super exponential distinguishability is at least such that it goes e to the minus n log n. So basically, this means that the error exponents are actually bounded by like a minus c log n growth. So actually, it grows like e to the minus n log n, or faster. How the errors go to 0. And okay, and to make a physical example of this, like these were like very abstract theorems, we could consider a Hamiltonian, which is this Hamiltonian that I'm showing. It's a simple XX Hamiltonian with a transverse magnetic field H. And it turns out that actually the ground state of these Hamiltonians are exactly or in the infinite spin chain are exactly type of ground states which can be obtained from the fermion, from a quasi-free fermionic chain via this Araki-Jordan-Wigner transformation, and they belong to very easy. I mean, then they have of course a symbol Q, and as we discussed that that if it's a translation invariant state, which it is, then the symbol Q is nothing else than the Fourier transform of a multiplication operator by a function, and this function will be just simply an interval, and the how big this interval is depends on the magnetic field. And just applying this theorem, we could actually make a corollary which shows that if we consider ground states, any ground states, for example, which belong to a magnetic field that is below, let's say, a value 80, and then other ground states that belong to this Hamiltonian, with the magnetic field which are bigger than, let's say, an H1, and H1 is strictly bigger than H0, then we could distinguish any of those these two set of ground states actually super exponentially. We were even able to give the operators that actually gives this super exponential error scaling. The POVMs that gives you the super exponential error scaling, and this is actually how we prove the theorems. So basically, in a physicist language, what you have when you are talking about these functions that define the Q operator, they are like the so-called it's in a quasi-momentum space, and they are the field modes. And then what we are doing is that somehow we are mimicking in a finite system the Fourier transform. We are doing a discrete Fourier transform, and we are looking at n spins, and actually sort of like building projections like these POVMs out of that. That's how we proved it. But the main result is that yes, we have easy examples for Hamiltonians and generic states where we have super exponential discrimination between the states when we are correlated. So actually, I have only 2-3 minutes left. So I would just conclude and give an outlook. So the conclusion was, of course, that these two scenarios, what I'm depicting here, that the IID case and the non-IID case we show that it can be qualitatively different. And I think we are the first one who came up with such strict theorems on that. And also we came up with physical relevant examples when this happens. And this is just the start of this line of research. Now we want to understand whether it also has some physical, whether there are some interesting physics behind this, or whether we can connect it more to many-body physics. One particular case that we believe could be true is that if there is a phase transition going on, let's say in a Ising chain, then you can maybe distinguish super exponentially the critical point from, let's say, some points that are non-critical, or maybe even two states in the two phases in this phase transition. For example, in the transverse field Ising model, which actually belongs to those ground states they are also quasi-free states and translation invariant, but they are not number conserving. So it's not exactly what we are treating, but we hope to be able to also move in that direction. So thank you very much. I don't know if there are any questions.
Thanks, Zoltan, for the very nice talk. Yeah, as Zoltan said, any questions from the audience, also feel free to write them in the chat. Nilanjana raised her hand, so please, Nilanjana, ask your question.
Hi, Zoltan. Thank you for the talk.
I
just wanted to make you aware that way back in 2016, Jan Potra, Kambiz Ruze, and I had already studied hypothesis testing in the non-IID setting. And in fact, we also studied the second order asymptotics. And one of the examples was indeed the same that you're considering, that of quasi-free states of a fermionic lattice gas. So maybe I can send you the reference.
Was it? May I ask you? Was it pure states or mixed states?
And we did not, in particular. It was mixed states. It was not pure states.
Yeah. For the mixed state, I would guess mostly it's still but please send me your paper. It's obviously relevant. But for mixed states, I believe mostly what you will see is, of course, like in other examples, they will be exponential separation, not super exponential, right?
Yeah, so we were not studying the question of super exponential discrimination, but what we did study was, you said that a non-IID situation wasn't studied before. We had studied it in explicit detail, including the second order asymptotics.
Yes.
Funnily enough, this quasi-free states in the car algebra of the fermionic lattice gas was one of our examples. Okay, so I'll just send it to you so that you can have a look.
Perfect. Thanks. Sorry,
okay.
I mean,
thank you very much.
Yes, of course, there were some studies already, and sorry that I missed your study, but
no problem.
There has been other by Funnes and others who also studied, but mixed states, and they haven't seen this super exponential one. That's what I wanted to emphasize.
Thank you.
Thanks.
Thanks, Dina, for the question. Any other questions from the audience? Well, if not, then I can maybe ask a question myself. So do you think this is tight, this log n, or do you think it could be even higher?
That's actually a great question. Originally, I didn't think it's tight, and I wanted to make, and probably we still want to make numerical explorations in that. We didn't, I have to admit. But now when we will wrote up the proof more precisely, it seemed that now I believe that it's tight, actually. But we should do numerics on this, at least, if not theorems.
I see.
Thanks for this question. Great question. I originally I thought, no, it cannot be e to the minus n log n, it should be e to the minus n squared, but no, I don't believe in one.
I see. Okay, are there any other questions? So if not, then let's thank Zoltan again for this very nice talk. And maybe I invite the next speaker.